Hi everybody, it's me, Dr. V, and it's a great day to review for the AP Chemistry exam. In this webcast, we're focusing on free response questions involving Coulomb's law and the best way to answer them. Now, there are three common situations involving Coulomb's law, three typical types of questions that we see in the AP Chemistry exam, especially in the free response. One is explaining periodic trends. We can also talk about strength of IMFs. And the last one is lattice energy, or talking about melting and boiling point trends for ionic compounds. They're all Coulomb's law. There's all little quirks that you have to know in terms of each one. So let's just do a quick refresher of Coulomb's law. The formula is actually on your formula sheet. The formula says that the force of attraction is proportional to Q1 times Q2 over D squared, where Q1 and Q2 are the charge magnitudes of the two interacting species, and D is the distance between the particles, really the distance between the center of the two particles that are interacting. So charge magnitude is a really important thing in terms of talking about this attraction. We don't have to do calculations, we just need to know this conceptually. What we see is that when we have a +1, -1 charge, there's a certain force of attraction. When we have a +2 charge for the cation and a -1 charge for the other species, notice that the charge doubles. What I really want you to take away from this is that as the charge magnitude of the interacting particles increases, the strength of the Coulombic attraction between those two particles also increases. The distance also is really important, right? So if we have two +1, -1 ions, and there's a certain attractive force between them, if we double the distance between them, we see that that force becomes less. Again, what I want you to take away from this conceptually is as the distance between the oppositely charged particles increases, the strength of the Coulombic attraction between them decreases. I do want to point out that the charges have a more dramatic effect on the strength of that attractive force than the distance does. So we always look at charge first and then distance. One of the types of questions where we need to apply Coulomb's law is explaining periodic trends. Let's start by talking about how to explain periodic trends that go from left to right across the period. We know that as we go from left to right across the period, the atomic radius decreases, and we know that ionization energy increases. We need to be able to explain why these trends occur, and we need to be able to do it in terms of atomic structure and Coulomb's law. So we want to talk about the trend in terms of the attraction between the nucleus and the outermost electrons. These questions will also often come with a prompt, discuss it in terms of Coulomb's law and principles of atomic structure, and that usually means you're talking about occupied energy levels, distance from the nucleus, and or the nuclear charge. I do want to point out that it's important when you are explaining trends that you don't restate the trend or discuss the position of the element in the periodic table. That's not going to get you credit. That does not demonstrate understanding. So as you go from left to right across the period, say as we're comparing lithium and beryllium, we're adding electrons to the same energy level. Lithium and beryllium both have two occupied energy levels, and that's an important thing to note. What we also see, though, is as we go from left to right, the nuclear charge, or the number of protons, increases. So I'm going from +3 to lithium to +4 for beryllium in terms of the nucleus. And as the nuclear charge increases, that means the outermost electrons are going to experience a stronger Coulombic attraction to the nucleus. And that's what I'm showing with these arrows here. Notice how it's thicker for the beryllium. And that means as you go from left to right, the outermost electrons are being held more tightly. And that means the atomic radius of lithium is going to be larger than the atomic radius of beryllium. It also means that the first ionization energy for beryllium will be larger than the first ionization energy for lithium. We can also use Coulomb's law to explain trends going down a group or a column in the periodic table. We know as we go down a column, atomic radius increases. We also know that ionization energy decreases as we go down a group. Why? Well, again, we want to talk about it in terms of atomic structure and the attraction between the nucleus and outermost electrons. I also want to remind you, don't use one periodic trend to explain another trend. If you are explaining why a trend occurs, you really need to come back to atomic structure and Coulomb's law. So to explain group trends for both atomic radius and ionization energy, we're going to think about what's happening to atomic structure as we go down the group. What you need to make note of is that as you go down the column, there are additional occupied energy levels, or shells. You need to really talk about them being occupied. As we go from period 2 to period 3 to period 4 to period 5, we're adding an extra shell, or an occupied energy level. And that means that the valence electrons are placed in occupied energy levels that are inherently farther from the nucleus. And that means the Coulombic attraction between the nucleus and the valence electrons is weaker, because there's a larger distance between the nucleus and the valence electrons. So that's going to give us a larger atomic radius. Because they're less attracted to the nucleus, it's going to take less energy to remove those valence electrons as we go down the column. In other words, the ionization energy will decrease. But making note that the valence electrons are in higher energy levels farther from the nucleus, additional occupied energy levels, that's what you really want to focus on in your answer. So to explain group trends just another way, again, we have more occupied energy levels as we go down the column. The valence electrons are further from the nucleus and they experience a weaker Coulombic attraction. Now, the College Board isn't really a big fan of talking about shielding. I don't recommend going in that route with your answer. I do want to point out that the electrons at an inner energy level don't have much of an effect on each other. The main effect really is that the outermost electrons are farther away from the nucleus. They feel a weaker attraction. Now, the next way that we often use Coulomb's law in AP chemistry is to talk about the strength of intermolecular attractions and to compare them. This is an important example from the 2025 exam, free response question number 1, part B, which asks you to explain, using Coulomb's law, why a sodium ion has a weaker attraction to water than a magnesium ion. And it was actually broken into 2 parts, based on the relative charges and based on the relative radii of the ions. So I want to point out in the diagram, we're shown an ion-dipole attraction between a magnesium ion and water. We're asked to explain why this particular attraction is stronger than what we would see for sodium with water. I do want to point out that you need to compare the charge magnitudes and the interparticle distance for this particular question, but it was broken out into 2 parts. We really need to compare the charges. You actually needed to explicitly compare them here and not just restate what we already knew. Magnesium ion has a larger charge magnitude, +2, than the sodium ion, which has a +1 magnitude. But we know from Coulomb's law, as charge magnitude increases, the strength of the Coulombic attraction increases. So the magnesium ion is more strongly attracted to the water molecule than the sodium ion is. That's the first part of the question. Then we had to talk about the relative radii of the ions, and this was a very tricky question for a lot of students. The common error that we saw was discussing the attraction between the nucleus and the outermost electron of the cation. And that's actually not what this question is about. To really think about any time you are using Coulomb's law that you specify which particles are interacting. And in this question, it's a cation with water. Thinking about our periodic trends, the magnesium ion has a smaller ionic radius than the sodium ion. And we just talked about period trends and why that's true for sodium versus magnesium. The magnesium ion has a greater nuclear charge. But that's really not the point here. It's not why is the magnesium ion smaller than the sodium ion. It's why are their interactions with water different? And for that, we have to talk about the interparticle distance. The distance between the magnesium ion and the oxygen atom in water is shorter than the distance between the sodium ion and the oxygen atom in water. And that's actually the essential point that you need to make here. And therefore, the attraction between the magnesium ion and the oxygen atom in water is stronger than the attraction between the sodium ion and the oxygen atom in water. So we talked about it in terms of the charge, and now we're talking in terms of the interparticle distance. We're really going from the center of the ion to the center of the oxygen atom. And that's really the key idea you need to have here. It's not at all about why are the sodium and magnesium ions having different radii. The other thing I want to say before I go on to the next part of this is that if you talked about the oxygen atom in water having a -2 charge, you weren't going to get credit. It's a partially negative oxygen. It's not an oxide ion, so be careful about those little details. We can also talk about strengths of IMFs and comparing them using Coulomb's law, because we can quantify how polar a species is. A more polar molecule will have a larger dipole moment, a numerical value. And that more polar molecule is going to have stronger dipole-dipole attractions than a molecule that's less polar with a smaller dipole moment. All right, so this all comes back to Coulomb's law, right? If we have larger partial charge magnitudes, we're going to have stronger IMFs. For example, 2 types of intermolecular forces present in liquid CH2O or formaldehyde are London forces and dipole-dipole attractions. Compare the strength of the dipole-dipole attractions in liquid CH2S to the strength of the dipole-dipole attractions in liquid CH2O. Explain. I think a good strategy here would be to start by drawing some Lewis structures. So here's formaldehyde, CH2O, and here's CH2S. They both have very, very similar Lewis structures. They both have carbon single bonded to 2 hydrogens. They have carbon double bonded to a group 16 element. They're both going to have a trigonal planar geometry. But that's really not what the question's about, although it does help to know that we are going to have these polar molecules. So we need to compare the strength of the dipoles. How polar are these molecules? And that really comes down to electronegativity differences. The carbon-oxygen bond is polar. The carbon-sulfur bond is polar. But that carbon-oxygen bond has a larger electronegativity difference than the carbon-sulfur bond. So if we represent those polar bonds with vectors, my carbon-oxygen bond is going to have a larger vector than my carbon-sulfur bond. All right, there's only one vector. They are polar molecules. That vector is giving us the overall polarity of the molecule, but the vector for CH2O is bigger, and therefore CH2O is more polar than CH2S. And from that, I can go on and talk about how the dipole-dipole attractions in CH2S are then going to be weaker than the dipole-dipole attractions in CH2O. The final place where we want to be able to talk about Coulomb's law is lattice energy, which is sometimes called lattice dissociation energy. And lattice energy is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So we can write it as an equation. We can talk about it in terms of particle level models. It's an endothermic process. I have to put a lot of energy in to take that ionic compound and get it to be ions in the gas phase. It's actually not something I can measure directly. We can do calculations to determine it, but it's not something you can just measure as such. Because it's something we can't measure, we often will talk about boiling points and melting points of ionic compounds as a proxy for lattice energy. And again, we can relate these to Coulomb's law because we have oppositely charged ions that are attracted to each other. The things we want to pay attention to are the charge magnitude of those oppositely charged ions and the distance between the centers of the oppositely charged ions. I do want to remind you, if you are talking about boiling points of ionic compounds or anything about ionic compounds, do not talk about single, double, triple bonds because they're not covalently bonded. And don't talk about sigma and pi bond because, again, it's not relevant for an ionic compound. So stay on track with that. Back to lattice energy. Here's a typical question you might see. As shown in the table, the lattice energy of KCl is less than the lattice energy of NaCl. Explain why in terms of periodic properties and Coulomb's law. We've got the equation, we've got the lattice energy, how much energy are we putting in. When you're doing these kinds of problems, anything with Coulomb's law, you first want to think about ion charges, and then we want to think about ionic radii. What I want to point out here is that both compounds have the same charge magnitudes. They both have a +1 cation and a -1 anion. So the charge magnitude is not the issue here. That's not what's causing this difference in lattice energy. It must be due to interparticle distance. The potassium ion has a larger ionic radius than the sodium ion. Why? Because the potassium ion has more occupied energy levels than the sodium ion. The key here is really that the potassium ion has got the larger radius. And therefore, the distance between the center of the potassium ion and the center of the chloride ion is larger than the distance between the center of the sodium ion and the center of the chloride ion. This is very similar to what we were doing with our ion-dipole attraction. First, you look at charge, then you look at interparticle distance. Therefore, the Coulombic attraction between the potassium ion and the chloride ion is weaker than the Coulombic attraction between the sodium ion and the chloride ion, and that's why we're seeing that KCl has a lower lattice energy than NaCl. All right, let's do another melting point lattice energy type problem. Which salt, potassium oxide or calcium oxide, would be expected to have the higher boiling point? Explain your answer in terms of periodic properties and Coulomb's law. Again, you first want to think about ion charges, and then you want to think about interparticle distance. I would expect calcium oxide to have the higher boiling point. Let's talk about why. So for potassium oxide, I have a +1 charge for the cation and a -2 charge for the anion. For calcium oxide, my anion charge is the same, but now the cation is +2. So I've got a larger charge magnitude for calcium oxide than for potassium oxide, right? The K+ ion has a smaller charge magnitude. And therefore, the Coulombic attraction between the calcium ion and the oxide ion is going to be larger than the Coulombic attraction between the potassium ion and the oxide ion. And therefore, the calcium oxide would have the higher boiling point. Let's just wrap up with some key points here. You want to make sure with these kinds of questions involving Coulomb's law that you correctly state which particles are interacting. Is it an electron to the nucleus? Is it an ion interacting with a molecule? Is it two polar molecules? Is it two oppositely charged ions? Make sure you identify that correctly, because if you don't, you're not going to be able to get credit for your answer. You want to then discuss the effective charge magnitude on the strength of attraction. Remember, it might be an actual ion or it might be a partial charge in a polar species. And then you want to discuss the effective interparticle distance on the strength of the attraction if those charge magnitudes are the same. First you do charge magnitude, then you do interparticle distance. That's what's going to help you every time. If you found this helpful, like the video and leave a comment, and subscribe to my channel so you get all my latest updates. Remember, keep studying chemistry every day. That's the key to success.